Hello.
Hi, everyone. Welcome to Finding Your Inner Modeler Conference. We're so excited to have you here today. My name is Jocelyn Tejeda, and I am one of the facilitators for No Innovation, and I am accompanied by my colleagues, Malachi Greaves and Donalyn Roxy, who you'll see in a bigger format on your screen. So we'd love to welcome you to an exciting week. We're excited that you're here. Our role is to really help manage and facilitate the event today. And so you have a number of content experts who are joining us. Please take the time to meet new colleagues, connect with old colleagues, and learn some new things as you're looking for new collaborators. So a couple things we want to share with you about working from home. And so we know that this is a very different time for us. And we know that it's always not easy. You know, you might have some interruptions, and that might look like family or pets. So all we ask is that you do your best. So when you're here, we do want you to be present or feel like you can be present with us. But we also want you to take care of yourself and your needs if needed. So please feel free to do that. The other thing is that here at KI, we have a saying that is suffering is optional. And so we know that Zoom fatigue is real and that people need breaks. So if at any moment you need to take a break, please feel free to do so. And then we'll just see you when you get back and handle whatever it is that you need to take care of.
Thank you, Jocelyn. So my name is Donalyn. We're going to kind of tag team the opening a little bit. And I would like to just tell you a little bit about our technologies and a few tips before we get started for our workshop. So KI has been running virtual workshops for a little over 5 years now, and we've collected a few things that we want to share with you. So first, congratulations, you've made it this far, which means you've seen our virtual venue, KaiStorm. You will be in KaiStorm all week. You'll find our networking lounges, all of our conference sessions, everything in there. The agenda is annotated, so we'll talk about that in just a minute. So as you're clicking through the agenda, not only will you be able to see what's happening, but we'll use that to capture questions and thoughts. So that's that yellow Post-it note. What you'll find is as we go through some of these activities, we will invite you to put virtual Post-it notes up. This could be during the social activities like speed networking, or pretty soon when we hear from Wallace for our first keynote of the conference, we'll invite you to add Post-it notes so that you can capture your thinking and share it with others. We'll also be using Zoom. However, I want to point out the Wonder Room. So if you joined us this morning for the informal networking, that room will be open throughout the week, 24 hours a day. So if you do see an old colleague and you're like, hey, let's have a cup of coffee or a margarita, whatever floats your boat, you can meet them there. It's always available to you. And then the last thing is kind of around tech support. So at any point in time, you can reach out to myself, to Jocelyn, or to Malachi. So you can shoot us an email, you can contact support@noinnovation.com, or you can just send us a chat message directly in this, and we will do our best to make sure that you can participate fully and not be limited by any of the technologies. Okay, so a few of the tips that we've learned, and we're really only going to share kind of 3 to get us started. One is the mic muted. So we will have lots of presenters and keynotes and project presentations throughout our conference. And while I think that Malachi is the fastest hands in the East at muting people, you can help us along and help us not be a distraction by keeping your mic muted when you're in the main plenary session. That would be nice. Next is to turn your camera on in small groups as you can and as you like. So we understand people have different preferences for cameras on and cameras off. Please feel no need to have your cameras on in the main plenary session if you need to grab a snack or anything like that. We totally understand. when you find yourself in small groups, one-on-one, or maybe up to 3 or 4, sometimes it's nice to have your cameras on so that you can see your future colleagues and have that connection. So as you like, we just recommend that. And our kind of last big tip is that everything is stimulus. So we will invite you, we're going to kind of pull you in KaiStorm onto different pages. So it's nice to keep that browser open. So although we will go into breakouts after our keynotes, if a question's burning in your mind that you want to capture, we've set up brainstorming via those Post-it notes on lots of pages. So be sure that you capture all of that awesome content while you're listening in this week. So the agenda.
Annalyn, I'm sorry, I have a quick question. How would someone add a Post-it?
Yeah, so we are going to get into that in just a moment. But if you, for a second, when Wallace is getting ready to talk for our first keynote, we're going to pull you to a page for Wallace. So great time to talk about it too, though. On the agenda, it is clickable. So you can click on this keynote by Wallace Marshall. You'll see a picture and a brief bio of Wallace. And there are Post-it notes set up right there. So if you have a question while Wallace is presenting, or when you're in those small groups, you can just pop it right there. There's a little plus button in the bottom right-hand corner of the pages that you can add Post-it notes to. Is that helpful? Yes. Okay. So the agenda itself, as we said, is clickable. So you can go in, you can see bios for people, you can see descriptions of talks where we have them. You can navigate starting tomorrow to look at those pre and post event lightning talks where you can see the abstracts. You can see abstracts for all of the poster sessions this afternoon. So please do use this. If you have questions while you're navigating, like, wait, I can't find this or see that, drop us a chat and we'll do our best to make sure that we can point it out to you. Because I'm sure if you have a question, other people have questions too. So an important thing to note about today's agenda that we just want to turn over really quickly, over the lunch break today, we're going to open up some concurrent session signups. So we just wanted to touch base on those really quickly on what that means. So there's 3 different concurrent sessions that will happen tomorrow afternoon. One is a Meet a Modeler, and that is a one-on-one conversation with an expert. I want to point out that the time slots are limited. Each expert only has 3 time slots available. And so please only sign up if you know for sure that you can be there. Because they are limited, we just really want to make sure that everybody can show up. The other 2 sessions are concurrent workshop sessions. So you'll sign up for either one of those. So you kind of have 3 different options to choose your own adventure tomorrow afternoon. We'll have an introduction to computational approaches for cell biologists. Or the kind of inverse of that is how to talk to biologists, tips for computational scientists. So we'll remind you again about what those are, but they are available on the agenda so you can look through them, and we'll tell you when we're going to turn that sign up on for you. Okay, I promise I'm almost done, and then I'm going to turn it over to Dave to give us our formal opening. A quick note about time. You will notice that we start exactly on time, and we are going to do our best to also end exactly on time. But our agendas will stay flexible to the conversations in the room. So at any given session, it might kind of move by 5 up to 15 minutes. And we just wanted to make sure that everyone knows that. If you leave and need to come back for any reason, feel free to capture or to catch up with one of the KI people, and we'll do our best to make sure that you know where we are in the agenda if anything moves. A few quick notes about who's here. So there's all of you. Woo, thank you. There's the KI people, which Jocelyn introduced all of us. You also have some presenters. So whether those are project presenters, lightning talk presenters, posters, our keynotes, etc. And then you have organizers / observers. And the reason why we wanted to call those out a little bit is that every once in a while, you'll find yourself in a small group and you might see, I'll pick on Dave for a second, kind of floating in and out of your sessions. I promise he's a really nice guy with a good sense of humor. He just wants to double check and see how the conference is going, how conversations are going, and things like that. So please feel free to welcome them into conversations or ignore them as you like. So I just kind of wanted to let you know that that might be happening throughout. And I think with that, that's all we have to share with you now. So please, again, feel free to chat with us if you need anything or send us an email. And I'm going to go ahead and turn it over to David Stone to have his welcoming comments.
Hi, I'm Dave Stone, and on behalf of my co-organizers, Elizabeth Stuhl and Michael Blinoff, I'd like to welcome you to Finding Your Inner Modeler Year 4, and also extend a virtual welcome to Chicago, where we hope to be next year in person. And if you're curious, I'm over here. I just want to say, when Donalyn was saying that I may pop in to your group discussions, I was asking them for an invisible cape, but they wouldn't give me that. Okay, so many of you have been to FYM meetings before, some of you haven't. For those who haven't, I want to give you a brief history of the meeting, an origin story, if you will. And for those who have been to FYM before, I want to update you on how the meeting has evolved. It's a little bit different now, the first 3 years versus now. This is not the FYIM meetings your grandparents or parents attended. So the next thing I want to do is give you a brief history of FYIM. Oops, that's the wrong book. All right, so the origin story starts in the spring of 2014. I was at a—
Did you want to be sharing your screen or just talking?
Oh, goodness gracious, I thought I was sharing my screen.
Oh, sorry.
All right, well, we're just gonna back up and I show you what you missed. And let me go back. All right, so the welcome to Chicago is there. I'm there. And now the brief history of FYIM. And that is the wrong book, sorry. Okay, a brief history of FYIM. It started in 2014 spring. I was at an NSF panel, and it was during a break. And for those of you who have served on NSF panels, you know the break is the time that you're working on 3 new panel summaries as a scribe. You're accepting comments and edits from your colleagues from the 3 you already have drafted, and you're sending out comments to them for their 6 summaries that they're working on, and signing off ultimately your approval of these summaries. So that's what we call the break at NSF. And I was enjoying my break when all of a sudden one of the program officers came over and sat down right next to me. She sat down right next to me. I can't tell you who this was, can't reveal her identity, but she sat down next to me and she put her hand on my knee. So I looked up and she looked into my eyes and she said, I really like what you had to say about computational modeling in the panel discussion. I said, you did? And she said, yeah, I really like that. And I said, I'm pleased. I'm very pleased to hear that. What is it that I said? And she said that I said that the proposals were just a lot of people throwing modeling aims, just attaching them willy-nilly. They weren't integrated well. They didn't really fit with the goals of the proposal. That the PIs had clearly gotten the message that NSF wanted to fund modeling. So they were throwing modeling aims at the wall, hoping something would stick and they'd get an award, just sort of tacked on. And I said, that's not really where we want to be. And she said, well, what we want you to do is write a grant proposal to fund a workshop to help cell biologists learn how to do modeling. And I said, I'm a little surprised you're asking me, because I was aware that NSF had just awarded a very large grant to Wallace Marshall. Wallace Marshall, who is really the Babe Ruth of computational modeling meetings and workshops. This was a very large grant at the time. It was 5 years to do workshops and meetings all over the country. So I said to this program officer, why are you asking me to do this? You've got Wallace Marshall. You've got the Babe. Why do you want me? And she said, well, you know, Wallace, that project, that's really the top-down experts, the people who already know how to do it. And I said, oh, so Wallace is the expert for the top-down people who already know how to do it. What you want from me is the bottom-up novice doesn't know how to do it. And she said, well, I wouldn't put it exactly like that. The way I would put it is you're our poster boy for someone who's gone from classical cell biology to doing quantitative cell biology, incorporating modeling in your work. You've really made the leap. You've transcended. She made it sound like the rapture. So after we talked a bit more, I realized that she was right. I had made that transition, and I probably would be someone who could write this grant. And moreover, her hand was still on my knee and her grip was getting tighter as we talked. So I realized also that I wasn't going to be released until I agreed to write the grant. So I did. So what I'm showing you here is the cover page for that first grant. And I want to draw your attention to the title, Finding Your Inner Modeler, How Computational Biology Can Advance Your Research and How to Get Started. So the point I want to make here is from the inception, FYIM was really designed to help classical cell biologists learn how to model and begin to use it in their work. And here I'm showing you a slide from the first meeting, one of the first slides, where I defined our goals of that workshop: to incite and inspire, to dispel myths about modeling, to instruct, and most of all, to catalyze collaborations. And drawing upon my deep model knowledge of modeling, I decided I would draw a network diagram, which is here, which shows a cell biologist and a computational modeler interacting at the workshop and forming a collaboration. But again, the emphasis was really about helping the cell biologist. And I want to say that in every one of the 3 FYIMs so far, the 2 in Chicago at UIC and the 1 in Alabama that Elizabeth Stuhl hosted at UAB, we always had a town hall meeting. And if you look at your agenda, the very last event of this meeting is also a town hall meeting. And in the town hall meeting, we basically ask the attendees, how did you like the meeting? What could be better? What would you like to see next time? And the message we started to hear in year 2 and continuing in year 3 was the modelers enjoyed coming to the meeting, but they were getting a little bit tired of serving cell biologists. Is that the only reason we're here? Just to help you guys? I mean, we have our own interests. So it was decided that a new grant had to be written, and this one would emphasize a community as a whole. Biologists and computational scientists of all disciplines working together to advance systems biology. And they asked me to write that grant, and of course I said no. And they said, wouldn't you please write the grant? And of course I said no again. And then there follows a black period in my life where I have no memory for about 3 or 4 months. I just sort of blacked out. But then when I woke up from that fugue, apparently I had finally agreed to write the grant. And what I'm showing you here is the cover page for the second one. And I will again draw your attention to the title. RCN stands for Research Coordinated Network. It's a type of NSF proposal. Finding your inner modeler in interdisciplinary community, solving problems in systems biology. So now the emphasis is on everyone, not just the biologists being babysat by the modelers, but developing a community where everyone can benefit. And if you look at the welcome page, I think this is well articulated, where we're talking about helping biologists get collaborators, but also helping computational scientists find biological problems they find interesting to work on. So that's the goal. Now, as part of that goal, this project includes not only the meeting, but also the meeting website, the FYIM website, which we call the Computational Biology Research Hub. This has been developed by Michael Blinoff at UConn. And it's kind of a funny thing. For many years going back, whenever Michael was turning out the lights of his office and leaving for the day, he would hear a voice. And the voice was saying, if you build it, they will come. And he really didn't know what that meant until he came to Chicago for FYIM2, and he learned about what we were doing, and he realized what he needed to build is this site. Now, later in the meeting on Thursday, Michael's going to have a slot to tell you all about this site, but I will just briefly tell you it has many purposes. It will post the meeting agenda. It will post talks with permission from the presenters from the meetings. It will post news. But the main thing is we want people to sign up to give their professional expertise, their interests, their projects, and we will use this platform as a way of forming collaborations, which I think is something that is really needed. So I encourage you to sign up and serve your country at this site, and it will, I think, be a very useful tool for the community. It will also look really good on my report to NSF if more people sign up. Now, at the very bottom of this screen, the first page, Michael, talking about this meeting, highlighted funding opportunities for new collaborators. This is something we put in the advertising poster, and it was money we asked for to help attract people to the meeting, and it's what we call training and travel awards. And you may wonder, how do you get a training and travel award, and what are they? Well, they're basically $2,000 awards to be used by you and your new collaborator for anything that will further your project. So how do you get one? You're eligible if you attend this meeting and you know the code word that I will say once during the week. So you have to go to every session and listen carefully for the code word. Just kidding, no code word. You just have to sign up for the meeting and be at the meeting. That's it. So you're already eligible. Secondly, you have to initiate an interdisciplinary collaboration this calendar year. And interdisciplinary really means cell biology using modeling as one of its tools. And usually there will be a modeler from a computational discipline, but that's not essential. The main thing is that you are collaborating with someone and using modeling. And in this calendar year means anytime during this meeting, after this meeting, or you could already have a new collaboration as long as it's brand new and you have not already published. All you have to do to apply is send me a less than 500 word description of your new interdisciplinary project and an NSF style biosketch for both you and your collaborator. Send it to my email by 11:59 p.m. on December 31st of this year. And this slide will be posted in the venue later, so you can come back and find this information. So we will make 10 of these awards. If fewer than 10 ask, all 10 will be awarded. If more than 10 apply, we'll have to make some choices, and you'll be notified and then instructed on how to sign up with the UIC payable system so that you can receive the $2,000 award to use for any training or travel that supports your collaborative project. So that's training and travel awards. Before I go on to introduce our first keynote, I just want to thank in advance, probably thank at the end of the week as well, our 3 keynote speakers. Greatly appreciate them taking their time to be with us, our 4 workshop leaders, and most of all, our 6 invited computational experts. I really am grateful for the time these guys are spending. They're really the heart of the meeting. They are going to be involved in all of the project presentations. They're going to do the Meet a Modeler sessions. They're going to be involved in the question and answer for the expert panel. So they're sort of the workhorses of the meeting. So a lot of gratitude to them. And then of course, all of you presenters, project presenters, poster presenters, and lightning talk presenters. We appreciate your contribution. And finally, of course, I have to thank NSF and the program officers who oversee this project, Richard Sear and Charles Cunningham. And now I think that brings me to the end of my welcome and introductory remarks. Am I on time, Donalyn? Okay, good. So that gives me plenty of time to introduce our first keynote, who is none other than Wallace Marshall, the babe. And Wallace, as you may or may not know, was our first keynote speaker at the very first FYIM. So there's a little symmetry here. Why is Wallace always my go-to guy? Well, if you look on your agenda, you will find, as Donalyn and Jocelyn mentioned, you can click and find out about every single organizer, steering committee member, and presenter. You can find their picture and bio. Wallace has written what I would expect, a very humble bio. I feel that I have to pump it up a little bit. I want to tell you a few things about Wallace. First of all, Wallace is an extraordinarily accomplished and productive scientist. He has published 13 high-level papers since the pandemic began, and 104 papers, or 105, since 2004. I could never get that number to come out the same twice in a row. So a little tip for future introducers, Wallace, maybe just put the number on that list of publications somewhere like 104, 105, whatever it is. Anyway, that's a lot of papers. Second thing I want to tell you about Wallace is that he was trained in electrical engineering and biochemistry and cell biology. So he's what I would call an interdisciplinary scientist. He's kind of the whole enchilada. He's someone who can auto-collaborate. And an example of his auto-collaboration I will show you on the next slide. I just want to ask if anybody has ever been lying in bed awake at night, unable to sleep, and thought, boy, what I really need is a high throughput device which will allow me to reproducibly bisect hundreds of cells a minute. Because if you've ever thought that, Wallace has got the thing for you. The cell biologist Wallace and the engineer Wallace got together and created what I think is probably the only cell guillotine in the world. And Wallace did not use this cell guillotine to put down a cell revolution in his lab. He used it to wound cells in a reproducible way so he could study how they are repaired. Wallace.
But in fairness, this was the engineer was Cindy Tang, so I was just really more of a spectator for this one.
Okay, well, so I stand corrected, but we still admire the work. Okay, so there's one more thing I want to tell you about Wallace before I send it over to him, and that is, I think you got the impression from the origin story that he's, very dedicated to promoting cell biology, computation in cell biology. In fact, I would say with absolute certainty that he is, that there's probably no one who has contributed more to promoting and popularizing computational approaches in cell biology. No one else with the name Wallace has done more than Wallace has. So he's definitely someone we can admire in that regard. But the last thing I want to say is that he also is not easily stopped. When the community needs him, he will be there. And as I mentioned before, he was the first keynote in the very first FYIM, but that meeting was not launched without difficulty. So the night before that meeting, which was July 13th, Thursday in 2017, a weather watch went up, and this was when everyone was traveling to Chicago. Major flood watch. The warnings was there were going to be heavy rains over an inch expected in Cook County, northern central Illinois. I was in a panic because everyone was flying in that night to Chicago. My co-organizer, Liz Haswell, wrote me the usual, "It'll be fine," but in fact, it wasn't fine. Hundreds of flights were canceled and delayed, and in fact, many of our speakers and participants couldn't get into Chicago. We ended up having a number of our speakers projected on a big screen by something we called teleconferencing. And I remember thinking, this is the only meeting ever where we've had to teleconference, and it will probably never happen again. Okay, so there's a little irony in there. But what was happening with Wallace? Wallace was sitting in a Dunkin' Donuts at Logan Airport for 6 hours, as the legend goes, 6 hours waiting for his flight, which he finally boarded and arrived in Chicago well after midnight. In the early hours, he got to his hotel just to change his clothes and get up, come to the meeting and give his talk. So I just want to say there's a word for such a person, and the word is one that is native to a tribe, a Native American tribe from Chicago. The Potawatomi use this word. Also, I'm told the Fox tribe and the Kickapoo tribe. They all have a word which they use for such a person, and that's mensch. So the Native Americans in this area would say, Wallace Marshall, he's a mensch. Okay, now I'm going to quit this slideshow, and I'm going to just fly you over to where Wallace is. So everybody hold on. That's where I am.
Dave, I'm not
All right.
sure. I think, Wallace, I think the floor is yours. We're
Okay.
running a
All right,
little.
let me see if I share my screen, what else, what's that going to do to, let's see.
That's all right. It
All right,
was,
can you see that?
we're on your screen, so we'll
Okay,
just
great.
dispense with that.
So that is very embarrassing introduction, Dave. I don't even know what to say to that. I wish half of what you said was true, but or even a tenth of it. But I really appreciate that your kind words. And yeah, that was an amazing meeting, and it was well worth all the Dunkin' Donuts that I had to eat. So yeah, and I'll start by thanking you, Dave, for making this whole series happen. I think it's a really great thing. So I'm really honored to be the opening speaker here, and what it's going to be an amazing session. So yeah, I don't even know how to respond to all of the great things you said, so I'm just going to go ahead and give my talk. So what I'm going to try to tell you about is some of the things we've been trying to do to learn about how cell geometry is produced, and the part of the work focusing on using simple models that make hopefully testable predictions. So if you look at cells, they have very complex and beautiful shapes. And although we know a lot about the components that they're made of, we know a lot less about how those components are put together to build these elaborate shapes. And in my group, one of the cellular structures we've been focusing on are cilia and flagella, which we like because they're relatively simple. They have a one-dimensional structure, so they're easy to measure. And I just want to make clear that I'm talking about eukaryotic cilia and flagella, not bacterial flagella, which are also very interesting. So we're talking about a microtubule-based structure with 9 microtubule doublets pushing out a protrusion of the plasma membrane. And so the geometry of this structure that we care about is how long it is, and that's basically fixed by how long these microtubules are. So we are doing our experimental work mostly in Chlamydomonas reinhardtii, which is a unicellular green alga. So we like Chlamydomonas flagella because they're linear. You can describe their shape by basically one number, their length. And we know that they use them to swim, so we know that the size directly relates to their fitness. And they're highly conserved. They're basically the same as cilia in a human. And we use Chlamydomonas because it's basically the closest thing to yeast that still has flagella. So you have yeast-like haploid genetics on all the genomic tools. So it's a very nice model system. So there's a lot of classical work on Chlamydomonas flagellar length control. And so here's a paper from Joel Rosenbaum, my postdoc mentor, published when I was a year old. And what he did here was measure the length of flagella in cells where the flagella have been popped off and now they're going to grow back. And so what he sees is that they grow back to their original length in about 2 hours. And if you actually look at this, so this is the length of the flagella at each point in time. And what you can see is that the growth rate is decelerating. So it starts out growing really fast, and then as it approaches the final length, it gradually tapers off. And the growth rate actually, if you fit a curve, is almost exactly 1 over the length. So this makes you think, well, maybe the cell knows how long the flagella are, and it's tuning the growth rate because it knows it's getting to the final desired set point. So the question is, well, how would the cell know how long its flagellum is? Can cells actually sense and measure size? So when we started this project, what we knew about flagellar growth is that it's a balance of assembly and disassembly. And this is work that I had done back as a postdoc. And what we knew was that the length of the flagellum is set by the microtubules, which are shown here in green, and the membrane is shown in the outline. And the tubulin is all made in the cell body. There are no ribosomes inside the flagellum. The tubulin is transported out to the tip where it assembles. And we could show that there's constant both assembly and disassembly. So even when you see the flagellum apparently static, it's actually a dynamic structure which is undergoing constant turnover. So you have this constant assembly and disassembly out here at the tips where the plus ends of the microtubules are. And we could also show that assembly requires an active transport mechanism called Interflagellar Transport, or IFT. And the reason why you need that is because all the protein is made in the cell body and it's got to be dragged out there by this motor system. So what is IFT? This is a kinesin-based transport where you have kinesin motors that travel along the microtubules. The kinesin motors grab a hold of a complex called an IFT particle. This is a complex of about 25 polypeptides. These polypeptides include docking sites for flagellar cargo like tubulin, dynein, other motors, other components. And so these IFT particles are like the bed of a truck in a sense. And these particles associate in linear arrays that are called IFT trains. So the kinesin motor pulls this IFT train out to the tip, cargo is delivered, then the entire train is brought back by cytoplasmic dynein in order to get more cargo. So there's a constant cyclic transport. So what we know is you have this microtubules that have to have their length regulated. You have assembly and disassembly taking place, and assembly requires transport. And the question is, well, what would you have to add onto this system in order to achieve a defined length? Well, whatever the system is, its goal is to make sure that these two rates, assembly and disassembly, equal each other only if you're at the correct length. If you're too short, you want assembly to predominate so you can get back out to the right length. And if you're too long, you want disassembly to predominate so you can restore yourself back to the right length. So the question is, what do you have to add to the system to achieve this condition? And so one thing that we knew from experiments is that disassembly is apparently length independent. So if you look at how fast subunits are being removed, that doesn't care how long the flagellum is. And it's probably because there's some machine sitting there pulling them off, like a depolymerizing kinesin or something, and it has no way of knowing how far away it is from the cell body. So disassembly is length independent. So therefore, to achieve this condition, you must somehow control assembly. And we also know that assembly is rate limited by IFT. We know this because of mutants. So if we dial IFT up and down, we can see concomitant changes in the assembly rate. So that raises the question, maybe IFT is somehow being regulated as a function of length. So how? So we know that when these IFT particles or trains leave from the base and move to the tip, they do so very processively. So anything that basically goes from the base into the flagellum is going to arrive at the tip to drop off cargo. So we don't think there's any real regulation at the level of speed or anything like that once you're inside the flagellum. The regulation has to be at the level of getting the IFT particles into the flagellum in the first place. So the question really is, what controls this step here of the injection of IFT into the flagellum? So several students in the group, Will Luddington and Ben Engel, did some quantitative imaging to get some numbers on this. And using turf microscopy, they could actually see these IFT trains coming in. And so these are chimegraphs where you have the line scan along the flagellum on one axis and then time on the other. And you can project those and see very nice quantitative plots. You can measure lots of cool features of these plots, but one of the main things you can look at is the frequency of these trains coming in, the speed that they travel once they get in, and then the amount of protein in each one based on fluorescence. And what we see is that as flagella get longer, the frequency of these IFT trains going in increases slightly, the speed increases slightly, but the big change is that the size of the trains goes down. There's less IFT protein per IFT train. And so going back to this idea that the train is a linear array of IFT particles, each of which is basically the bed of a truck that can bind cargo, what we see is that in short flagella, the trains are very large. They have many, many copies of these IFT particles on them. Therefore, each train can carry a lot of cargo. And then as the flagella get longer, we see the trains become smaller and smaller. So these IFT particles remodel into into smaller trains, which have less cargo capacity per train. But I think the cargo capacity per particle is still the same, and we can talk about that later if you want. So the interesting thing is that if you multiply the frequency of these trains coming in by the size of the trains, that gives you the total injection rate of the IFT particles themselves, which are what determine the rate of assembly. And that goes as 1 over the length, it turns out, when you multiply these two curves together. So this exactly matches what we saw for the growth rate. So that suggests a model like this. Here we're plotting rates versus length. And we see that the disassembly rate is length independent, so you get a horizontal line. The assembly rate is going as 1 over the length, so you get a hyperbola. And there's only one length where these two curves intersect. And that gives you a steady state solution. And this is a stable solution. If length gets too long, disassembly predominates and you shorten. If length is too short, assembly predominates and you'll grow back out. So if you take this kind of model, first of all, it predicts a unique stable length, which is good. It also exactly predicts the shape of the regeneration curve I showed you at the beginning, where the flagellum grows at a decelerating rate that goes as 1 over the length. It can actually explain other phenomenon too. So there's been this classical phenomenon of flagellar length equalization in Chlamydomonas. So each chlamys cell has 2 flagella, and they're usually exactly the same length. If you chop both of them off, they regenerate according to that curve that I showed you. But you can also chop just one of them off, and this can be done using laser ablation, or in the old days you push on a cover slip with your finger until just one flagellum pops off. And what you see is that as the flagellum that popped off grows back, the other flagellum that you didn't touch starts to shorten. And it will shorten and shorten and shorten until they reach the same length, and they grow back out together again. And this is just showing you what this kind of data looks like. This is, again, from a paper from Joel Rosenbaum, length versus time. The short flagellum grows out, shown here in the white dots. And at the same time, the long flagellum shortens until they equalize, then they continue growing back out together. So the classic interpretation of this experiment was that somehow the long flagellum knows it's too long, and it makes itself shorten because it thinks it's too long. Question is, can our model account for this in a simpler way without having to invoke communication between the flagella or some kind of cognitive process inside one of the flagella? So if you think about the 2 flagella, they're actually in competition for a common cytoplasmic precursor pool of tubulin and other proteins, right? So each flagellum is dynamic structure. It's taking up tubulin, but it's also returning tubulin as it disassembles back to the cytoplasm. Now, normally the 2 flagella are equal in length, so they're able to compete in sort of a fair way on a common footing. But suppose, so normally both flagella, say, are operating at this steady state position here of rates versus length. Suppose now one of the flagella gets a lot shorter than the other because we chopped it off. Now, because the assembly rate is 1 over L, a very short flagellum will grow very, very quickly. That means that this flagellum is now grabbing more than its fair share of the precursor pool. And so because the other flagellum was hovering right at this balance point, it's going to have to shorten because it has less tubulin to build with. So we can build computational models based on the kind of graph that I showed you before, and indeed recapitulate what we see in experiments. So as the severed flagellum grows back, the long one shortens, and they grow back out together again. So we can predict this equalization of length that people had seen, decades ago. So that was good. It seemed like the model could predict what was known. But then after publishing this model, someone came up to me and said, look, there's this paper that actually contradicts your model. And this is a report from John Jarvik in the 80s saying that if you make mutants of Chlamydomonas that have variable numbers of flagella, and this is why it's great to work in the genetic model system because you have all these mutants available. So there are mutants called VFL, a variable flagellar number. And what Jarvik did was to measure the lengths of the flagella in those mutants. And what they reported was that no matter how many flagella the cell had, they were always the same length. And so it was asserted that this contradicts our model because if there's more flagella, they should be competing with each other and they should all get shorter. So the question became, well, exactly what does our model really predict? And the more I thought about it, the more I thought, well, we don't really know. Let's try to use math to figure out what the prediction actually is. So the question is, do we predict this result or something different or what? So going back to this diagram I showed you where we have rates versus length, we can convert this into a differential equation shown down at the bottom. And I'm just going to go to the next slide to discuss that. So here we're plotting the rate at which the length is changing, so the growth rate of the flagella. And we think it's basically the difference of these two terms, the first of which is describing the growth process. So A is just some constant that incorporates a lot of things that we want to lump together, like how fast the flagellum elongates as a function of tubulin concentration and so on. P minus NL. N is the number of flagella, so and P is the precursor pool. And this incorporates the idea that the more flagella you have, the less available precursor there's going to be to keep building with. And then L is the length. So we're dividing by L to incorporate that 1 over L dependence. And then we subtract the disassembly rate D, and this is indicating that disassembly is length independent. So we have this differential equation, and we would like to know at that steady state, that is when the flagellum is finished growing and everything's just sort of equilibrating, what is L as a function of N? So let me just take a moment to discuss differential equations. So these are something that come up a lot in modeling, and depending on your background, this may or may not be something that you feel familiar with. And so usually they're written something like this: dx dt equals some function of x. And what I want to say is that for many of us in biology who think we are not used to differential equations, actually we are. Think about something like the Michaelis-Menten equation. It is literally a differential equation. It's just that it's not written that way. So the idea is that here, V is actually the rate of change of the product concentration as a function of time. So this is actually a differential equation, right? So V is just d product dt. So whenever you see a differential equation, if it's not something you're familiar with, I would just linguistically replace it with the phrase rate equation, and then you'll not feel like it's something so strange. Okay, so we have this differential equation or rate equation, and we want to solve it for L as a function of N. What on earth do you do? So the classic way to do this, what people might tell you is, well, you use calculus, and so you basically solve this, integrate out the time. So you solve for L as a function of time, you get some kind of a curve, and then you let time go to infinity and ask, at the end of the day, when everything's settled down, what value of L do you get? I do not advocate this as a general way to solve these things. Yes, you can do it, and you might want to know this information in some cases, but if all you want to know is the final steady state solution, there's a much easier way to do it, which is that steady state means that nothing is changing, right? That's sort of definition of a steady state solution. And so what you do is you just set the rate term dl dt to 0, right? So here we take our equation, set that to 0. Now we just do some algebra, right? We move the d over, we multiply both sides by L, and there's probably even a faster way to do this. I don't know, this is just how I do the algebra. And then we get all the terms with L on one side, then we divide everything out. So at the end of the day, just by doing algebra, no calculus whatsoever, you get that L is the total precursor divided by the number of flagella plus the ratio of the disassembly and assembly constants. So if you knew the value of all these constants, you could find what L is as a function of N. So the great thing is we can then take this solution and try to fit it to actual data, right? And that is just by using algebra and no calculus. And when we fit this to actual data, this is data that we ourselves measured. I mean, I did this actually during Christmas vacation one year. This is the length of the flagella versus the number of flagella in the cell. We can get an extremely good fit to the measured data. Now and what we see is that indeed it is the case that as the number of flagella goes up, the length goes down. So why did Jarvik claim that this was not the case? If you actually look at Jarvik's paper, in one of his mutants, for the first few values of N, they're kind of the same, but then they still go down later. For the other mutants, there's a very similar dependence to what we see here. And this is kind of interesting from a modeling point of view. Jarvik in his mind had a model where all the precursor was being incorporated into the flagella. So if you had twice as many, they should be half as long. So you just have a geometric dependence. So every time you double the number, you should have the lengths. And that's not what we see, right? It's not as steep a dependence. So he saw that it was not such a steep dependence and concluded that it was independent in the title of his paper. So this just shows, I think, that even just looking at your data, the way you interpret it depends on the model you have in mind. So we end up with this model that we really like. It can account for a lot of things. It can explain the regeneration curve. It can explain equalization of the two lengths. It can account for this result of L versus N when we use our algebraic method to get the steady state solution. So that's the good news. It can explain sort of everything that had been published. But the bad news is it relies on this fact that the injection of I of t is going as 1 over L, and we have no idea why that is. So the model really doesn't actually explain anything. It just changes the problem. The problem now is not how do you decide how long the flagellum is. Now the problem is how do you make the flagellar length scale as 1 over the length. So this is the challenge now that we've been facing in the lab is a lot of our work is focusing on what determines this 1 over L rate of injection. And I should say that when we first were working on this, the model I liked was that maybe there's nothing that determines this. Maybe when you first build the flagellum, you load up a fixed number of particles, and the particles just circulate back and forth like subway cars in a subway system. And the nice thing about that kind of a model is that each particle has to go out and back, and the round trip scale time goes as the length. So therefore, the round trip frequency goes as 1 over L, and you can actually explain everything that way. The problem is that the assumption of that model is entirely wrong. The IFT particles are not trapped inside. They exchange very rapidly. They come in, travel, go out, come back, and then back to the cytoplasm again. So there's got to be some kind of mechanism which is controlling the injection in here. And whatever that is, it's got to go as 1 over L. So the model we think now is that there's something sensing the length of the flagella, and that's regulating something that happens at the base. Now, whether it's opening and closing a pore like a nuclear pore, there's some evidence from Kristen Verhey and others, there's a nuclear pore-like structure at the base, whether it's recruiting, modification of the IFT trains by phosphorylation. There's some work from Junmin Pan's lab at Tsinghua, which suggests that kind of mechanism. We don't really know what's going on at the base. So you can imagine then all kinds of models for how this works. And actually this question reminds me a lot of the classic question in physics of how do you measure the height of the Empire State Building using a barometer, right? And what the teacher wants you to do is go to the top, drop the barometer off, and go to the top and measure the pressure differential. But what you could do is drop the barometer from the top and measure the time it takes to fall. You can make a pendulum out of the barometer and measure the frequency of the swing and so on. So there's many ways to solve the same kind of problem. And so sort of the exercise we're engaged in now is coming up with ways to measure that we can imagine to measure the length of something using molecules and then testing those. And we've now ruled out several of the kind of models that we were thinking about. I'm not going to go through them. I'm happy to discuss that during the question session. I will tell you the model that we currently favor, and we currently favor it because right now we have no evidence against it. So that's really all I can say. The model is as follows. I told you before that the IFT is driven by kinesin. So you have kinesin motors that are carrying these IFT trains into the flagellum. Then the trains turn around, they're brought back by dynein. How do these motors traffic? Well, we know that dynein is actually brought out as part of these IFT trains in an inactive state. So it's basically dynein itself as a cargo on these anterograde trains. But interestingly, if you look at kinesin, it is not a cargo of the retrograde trains. You do not see it moving back powered by this dynein motor. Instead, what happens, this is work from Ahmed Ildiz at UC Berkeley, the kinesin actually appears to get back by diffusion. So it pops out off at the end of the flagellum, and then it diffuses back to the cytoplasm. So that's interesting because diffusion has very interesting scaling properties as a function of distance. The longer you are, the way the time it takes to diffuse back scales with distance is quite different than if it was moving as a motor. So my student Nat Hendel started out by making what we call an agent-based model. So he wrote a computer program that represents, basically it's like a video game, represents each element as a character or something in the game. So each motor is represented by an object, each IFT particle. We have tubulin representing the growth of the microtubule. And then he has rules saying, okay, at each time point, the motor, if it's engaged with the microtubule, will take a step forward. If it's popped off, it can randomly take a step forward or back. And meanwhile, we model the cargo being brought out and disassembly. So the entire thing can be modeled. And the nice thing is that this really, you just directly represent the assumptions you have in the computer. You don't have to know how to solve anything mathematically. You let the computer tell you by simulation what the result will be. And so the result is that this kind of model seems like it can work. You can get, at steady state, you establish essentially a linear gradient of kinesin as you'd expect for a diffusing system. If you look at the injection rate of IFT, it drops off as the length increases. And then if you look at lengths versus time when it regenerates, it does this sort of decelerating kinetics. One thing which is different than our measurements is that the injection rate is going as 1 over L squared, not like 1 over L. But it's not clear that our data can really distinguish those. So it's really focusing our interest on that. We started out by making this agent-based model because it's easy and it's a way to get to find out, is your basic idea of even remotely valid? And then, it's kind of unsatisfying in a way because you don't intuitively see how varying parameters will affect things. And so at a cell modeling hackathon we did, my student Nat teamed up with Hongmin Chin at Texas A&M and Ray Ma from Yale to make a more of a differential equation type model where you can actually solve it for steady state without having to run simulations. And so now we think we have a much clearer view of how various parameters contribute to the final solution. So right now, all data we have suggests that this model might work. The way to test it is to change the diffusion constant of kinesin. And that's unfortunately very difficult. It's hard to know how to modify the diffusion constant of a protein. This is a very large protein, so just sticking on a couple of GFPs doesn't really change the diffusion constant very much. So we're currently trying to see, is there a way that we can put something like an anti-GFP nanobody onto the flagellar microtubules and then make them sticky for the kinesin and then tune the diffusion constant that way. So that's where we're going with this project. So I just want to close with a final thought, which is why bother using simple math? So what I've tried to show is that you know, I don't really know very much math, and I've been able to, we've been able to make pretty good progress without knowing tons of advanced math. And you might say, well, why bother? Why not just collaborate with an expert? And I believe this question, why try to do your math yourself as a biologist? Why not just collaborate? That is a totally false dichotomy, and I hope everyone will agree with that by the end of this conference. Obviously, you can and should still collaborate, and we've had fantastic collaborators working on this project. So Yannick Kondev and I have collaborated on modeling the fluctuations of length, and I mentioned Remark collaborating on making an analytical version of the diffusion model. But these collaborations were greatly facilitated by the fact that we'd already tried our hand at it. We already had an idea at a very crude level of how we could model things. So then we could talk to these real experts at a level that they would find interesting, and we could understand something about what they were saying. And I really think that in many respects, mutual understanding is the key to having a good modeling collaboration. It allows you to reality check the results of the model, but also the assumptions of the model. And it also, I think, would allow the biologist to have some idea about why is the modeling person asking me certain questions, and conversely, the modeler can understand, well, why is the biologist saying certain things that may seem irrelevant if they didn't know something about the biology. So I really believe in mutual understanding here, and I also think we want to sort of break the culture of dependency. And this again goes both ways, kind of like what Dave said, how there's a tendency for people to want to view the modelers as someone who's going to just serve them and model for them. And I don't think it really works that way, at least not well. It works much better if it's people working together. So I want to close by thanking the people in the group who've been doing all this work. We've had I've been blessed with an amazing group of people in my lab, and also fantastic collaborators who we continue to work with, and our funding sources. And it's great to have you all here listening to me, and I'm happy to take any questions when we get to the Q&A session. Thank you so much.
Awesome. Thank you so much, Wallace, for that wonderful presentation. If we could give Wallace a clapping emoji to show our appreciation, that would be great. So here's what we're going to do next. What we're going to do is that we're going to put you in small groups between 3 and 4 people. And what we're asking is that, one, you introduce yourselves to one another, and that you have a discussion around what are some questions that came up as you listened to Wallace's presentations, and what are some questions that you have for him. And the way that we're going to capture those questions are on KaiStorm. So if you remember earlier, Malachi sent everyone to Wallace's keynote page. There on the bottom right, once again, you will see the plus symbol in which you can add questions. We actually already have a few of these here for Wallace. So again, we'll send you out into small groups. You'll have about 15 minutes to introduce yourselves and then to post any questions you might have. And just a friendly reminder that you want to post 1 question per post-it. So Malachi, are we ready to send everyone out?
In just a moment. Just a second. My apologies. Okay. Yes, I will send everybody out. Would you like to let them know when they'll be returning?
Yes, so in about 15 minutes, yeah.
Okay, see everyone back in about 15 minutes.
All right, enjoy the conversation. We'll see you back in a bit.
We are going to go ahead and spotlight Dave and Wallace and let them start going into some of your questions for you.
Okay, well, Wallace and I have been looking at the questions as they're posted, and Wallace has already stated that they're all very good and interesting questions. So I am going to let him pick out the ones he wants to answer. And if he goes on too long, I'll interrupt and say, move on, Wallace.
Okay, sounds good. So yeah, so I don't even, these are also good. Let me just kind of, I guess, randomly tackle these. So yeah, so one question which I think is good to get is, the question was, do we know the number of Kinesin motors in the flagellum? And do we use that in the model? And one thing that, in many cases, you don't really, I would argue the exact numbers may or may not be relevant. It depends on the kind of model you have. And some people I know really are obsessed with measuring exact numbers. Other cases, all you really care about is how the numbers change under different conditions. That is, how does the number change as a function of length or so on. It does happen in the case of kinesins. We do know the number. And the way we know is that we have GFP tagged kinesins. And what we can do is we can fix the flagellum and do stepwise photo bleaching. So you see, a step every time you bleach one of the kinesins. So that gives you in my mind, that's one of the nicer ways to know number, because it doesn't depend on exactly estimating the fluorescence per GFP, which you can also do using, the appropriate standards. So in that case, yes, we are using what we think are pretty realistic numbers for the kinesin. Now, the flip side of that is the kinesin is only part of the story, right? You've got the kinesin plus these IFT particles. It's not entirely clear what the stoichiometry is of the kinesins and the IFT particles. Is it one particle per kinesin? Is it one kinesin per train? From some of the cryo-EM work, it's looking like it's probably one kinesin per particle, but different people have different numbers for that. So I would say we know some of the numbers, but not all of them. And I think, what we would like to do is have it more like, the kinetochore, where in yeast, where people have done very careful measurements of basically the numbers of all the components, in case any of them vary in some interesting way. I mean, the interesting thing would be, are there some of the proteins that don't scale as 1/L, or in the way that our model would predict, and then those might become sources of regulation. So, but for kinesin, yes, we do have the numbers.
Can I ask a quick follow-up question?
Yeah.
So given that you know that number, you must have run the model varying it over folds. And how critical is that value? Is it robust?
Well, right. So that feeds into So if you have more kinesins, assuming the cell can provide those with more IFT particles, then you can get longer flagella. But basically you end up have to make assumptions about how the number of IFT particles might change when you change the number of kinesins. And that's something that we don't actually know, and I think which should be tested experimentally. And this leads to, I think there was another question about, can we vary the amount of the kinesin motor, say by overexpression? And that's something that we haven't really, so kinesin motor, or can we vary, for example, the amount of tubulin by overexpression? The tubulin we've tried, and it's actually very, very, very difficult to vary the quantity of tubulin in a cell, because there's this post-transcriptional autoregulation, so that if you upregulate the gene, you just downregulate translation, and the total protein you get ends up being the same. So our attempts to increase the amount of tubulin have not succeeded. For the kinesin, we haven't really tried that. It's a heterotrimeric kinesin, so you'd have to overexpress probably all 3 subunits to make more of it. Doesn't mean it can't be done. It would require, some relatively heavy lifting on the molecular side. Chlamydomonas is a great system in many ways, especially for classical genetics. It's not fantastically great for expressing transgenes, in the sense that you often get silencing to various degrees. And so you'd have to not only express all 3 genes, you'd have to make sure you had a construct where they were all expressing at a high level. It can totally be done, but it would require someone really dedicated to try it. And we just haven't tried that yet. So that was so there were several questions along the lines of varying concentrations or overexpressing. I do think that would be worth doing if we could do it, but it's going to be hard. Let's see, kind of along the same lines, could we maybe inhibit some of the enzymes? So for example, could we inhibit the kinesin? Yeah, in principle, you could. So what we can inhibit is the dynein. So the cytoplasmic dynein can be inhibited by a compound called Cilia brevin that others identified. The results for that are I would say very confusing and strange, in the sense that what we see when we inhibit the dynein is yes, you stop having retrograde traffic of IFT trains. You continue to have anterograde traffic of IFT trains going in, which mimics what we know from, in my lab, we made, Ben Engel, my student, made a conditional mutant in the dynein. So you can raise the temperature and turn off the cytoplasmic dynein or slow it down. And what he found when you slow the dynein down is that you basically you keep pumping IFT in, but it comes out more, the IFT trains come out more slowly, so they begin to accumulate inside the flagellum. So the dynein you can play with. The inhibitors for dynein are weird though, because Cilia brevin has a very short half-life in the media that we grow Chlamydomonas in. So you add it you only see the effect for a couple of minutes and then it goes away. So we tried to use this as a tool, but essentially the way we were doing it, which is to dump it on and then mount the thing on a slide, by the time we were getting images, it was already really too late. So I think we need to go back and use microfluidics to just squirt the Cilia brevis on just at the last minute while we're imaging, and we haven't done that yet. So I think that's a pretty cool experiment. Actually, looking at the questions, my answer to almost everything is that these are great questions, and we want to work on getting answers. So that may not be very satisfying, but yeah.
What about number 6, the flagellum
Number
activity?
6. Oh yeah, I love this question. So does flagellar activity affect diffusion rate? So one of the reasons why I love this question is that so Chlamydomonas has been used to study flagellar motility extensively for many, many decades. And so there's lots of mutants that paralyze or otherwise impede flagellar motility. Almost all, not all, but almost all of the paralyzed mutants also have short flagella. And so that makes you wonder, is there something about flagellar motility that's contributing to the ability to grow longer? And so when we had this diffusion model, indeed, we got very excited about this idea. And actually, the way we started working with Ho-Min Chin and Remark was at this hackathon where Dr. Chin is an expert in flagellar motility, among other things. And so we decided, well, let's, is there some reason why the motility could affect diffusion? And so we basically decided to spend some time brainstorming all the ways that flagellar bending and motility could affect the diffusive return of the kinesin. So one model that we had that I really liked is a centrifugation model. So the idea would be, so this comes from the observation that actually Dr. Chin made, which is the IFT particles are less dense than the soluble media of the flagellum. So if you pop flagella off, concentrate them, and lyse the membrane, you can then get a dense extract. And if you spin that thing, the IFT particles float to the top. So they're less dense than the rest of the media. So if you were to centrifuge them, that would drive IFT particles going to the top. So if you imagine the flagellum as basically a tube in a centrifuge swinging around like this, the centrifugal motion should drive the IFT particles back to the base. And so the idea was, well, if that's true for the kinesin as well, and I think actually she did know the kinesin also floats, then those proteins would be driven back. So they wouldn't have to return just by diffusion. You would have this faster rate of return from centrifugal forces. And that would actually allow you to grow to a longer length, such that when you turned off that motion, you would have to return by diffusion, and then the flagellum would become shorter because it couldn't get kinesin back fast enough to continue growing. So we did a calculation though, and we had a lot of numbers here about the density of the components and the rotational rate of the flagellum. And the prediction was that, yes, it's true, there would be a drift factor that would cause the kinesin to come back a little faster than it would by straight diffusion, but that the time required for a single kinesin to get back would be something like 70,000 years. And so that was a case where, we talk sometimes about how the numbers don't matter, just, model the general principles. This is a case where the numbers really tell you that the model just can't work, even though, it works in some sense, but in reality, it wouldn't apply. So we don't think it's centrifugation effects of the flagellar beating. What's possible though, is that the soluble medium, the fluid phase of the flagellar compartment is extremely crowded. It's highly dense in protein. The proteins are moving through this complicated molecular structure of the flagellar axoneme. And so it's this crowded protein mix, and some crowded protein solutions show shear thinning, where if you basically shear them back and forth, you actually change the viscosity. And so one possibility is that we're seeing shear thinning. And what we did was, if we assume that the flagellar liquid phase is like other shear thinnable biological media, then in fact you would be able to explain the length variation you see in the paralyzed mutants. The problem is that some paralyzed mutants don't have short flagella, and so then we have to explain that. So I think at this point, all we would say is it's worth considering more about the shear thinning effect. What we'd love to do is measure the diffusion constant of kinesin in a beating flagellum. That's extremely hard, right? All the measurements anyone's ever done are in paralyzed flagella, because otherwise, if they're not just sitting there, you can't actually measure the diffusion. So if anyone has a good way to measure diffusion constants in a rapidly moving object, I would love to hear about that. I think with technology going the way it is, there's probably going to be some really clever, I don't know, light sheet way to do it, but we have not been able to make that measurement. Dave, should I just keep picking questions, or you want to?
Yeah, go ahead.
Designate them. Let's see. Oh yeah, so question 8. I'm just going sort of in reverse order. how can you distinguish between 1 over L and 1 over L squared delivery rate? Yeah, so this is the problem. So what we can do is we can look at flagella of different lengths and we can quantify the injection rate of the particles. The problem is when the flagella are too short. So we do this by turf microscopy. So the cells are sitting on top of a cover slip, and the flagella splay out, and then we can watch the particles coming in. The problem is if the flagella are less than a micron or so, first of all, the cells don't really adhere very well. And even if they do, the cell's kind of sitting like this with the flagella are pointing downward. So you can't really resolve the traces coming in. So you can only see IFT once you've gotten beyond about 1 or 2 microns of length. And then the total length they're going to grow to is only going to be about 10 microns. So you're only looking at, 3 to 5-fold range. And so if you're trying to fit some curve where you only have a several fold variation on the x-axis, it's actually can be pretty hard to determine what the shape of that curve is, whether it's linear or x squared or x cubed or whatever. So I would say right now, it is true that if we just take our data at face value and we plot the data points as we get them, the best fit is 1 over L, but a 1 over L squared fit is not that bad. What we need to do is increase first of all, if there was a way that we could measure this in very short flagella, that would be extremely helpful. And so, we think we can do this. We've made a microfluidic device where instead of cells sitting in splayed out on a cover slip, the cells sit sideways with the flagella coming out over a little PDMS table, so that we can see the entire flagellum all the way to the basal body in focus. And that can allow us to make measurements of shorter length flagella. But then to address the longer length flagella, what we'd love to have is mutants that make flagella that are longer. And there are such mutants. The problem is all the mutants that we have that make flagella longer appear to do so by increasing the IFT injection. So there's more IFT particles coming in. So we don't yet have a mutant that will allow us to make longer flagella without also messing with the IFT system. But I think even going to the shorter ones, if we could go from 2 or 3 microns down to 1 micron or half a micron, that would sort of double the range that we the fold variation that we could plot over.
Can I ask
Okay,
a
yeah.
general question, Wallace?
Yeah,
I'm going to throw in one of my own questions.
yeah, please.
Obviously, a theme of your talk and your other talk at FYI was simple math, and you don't need. And I'm just curious. I mean, you definitely, when you talk about your math, I'm certain you've done calculus. Yes.
Well,
But,
yeah.
Yeah,
At some point.
Nothing beyond that. Is that what you're saying?
What you mean, like in our lab, in our work?
No, I mean coming in as a PI that's using modeling, encouraging others to start with simple math. How far does your math go?
Oh, me personally? Well, so yeah, that's a good point, because I was a double E electrical engineer, and so we did a lot of math in double E. However, the math we did was all of a certain type that unfortunately, in my experience, hasn't really applied very well. So everything in double E, essentially, at least at the level that I did it, is basically linear. So you basically you set up a bunch of linear equations and then you solve them, and so we do Laplace transforms, which are great if everything's nicely behaved. So we did a lot of math, but I haven't really. It wasn't math that I personally was able to bring to bear. I thought I could, right? In the early days, I thought, oh, this is great. I'm going to model feedback control systems with Bode plots, and it's going to be awesome. And then I realized, well, biochemical pathways just don't look. They're just not nice straight linear amplifiers. And so I know there's people who try to do this. I think people who are in much better position to do that would be mechanical engineers or chemical engineers, where they're used to dealing with these weird, nonlinear things. So I feel like, yeah, I learned a lot of math, but it maybe was the wrong kind of math in retrospect. I don't regret it. I loved the classes I took, and I still like electronics as a hobby. But I think I do think that just getting an experience with any kind of math is still useful, because it makes you able to pick up new things. So I've been trying to teach myself more dynamical systems kind of approaches, but it's all stuff that I've been sort of trying to self-learn. But I think having done a bunch of math of a different kind at least lowered the activation barrier to doing that. But I think people from a more chemi kind of background or physical chemistry are probably in a stronger position. But we've gotten pretty far, and I'm okay. I'm able to puzzle along, and if someone helps me out, one thing that's helped is actually my father is an applied math professor, and so occasionally I would ask him questions, and that was actually very painful, because first of all, he would yell at me for not being able to explain what I'm doing in a way that a sane person could comprehend. And I think, a lot of the things that you get when a lot of these collaboration fails, we sort of experience within our, me and him trying to interact. But after all, he would like point me in a good direction. So I have personally experienced the situation of having someone who you can talk to and who can just point you to what you might want to do. And then you can go and figure it out by, yourself. So like, that worked out pretty well, actually. Once the yelling stopped.
Donaldin, how much time do we have?
You have at most another 15, at most. But I also realized that, Eric, did you have a follow-up question?
Yeah, but I'm sorry, it's actually a little difficult for me to type in this current setup that I have. I don't
Go
have good
for it.
Verbally, yeah,
so
just
I
say
thought
it.
I would just ask. Okay, so wow, this is fantastic, really interesting. And I think a really great example of how you can have like small, like equilibrium or steady state algebra and you learn stuff. It's really cool. But the question I had is that it looked from your earlier data, like the thing that was changing most was not the frequency of the motors going in, but rather the amount of stuff they were carrying. And the model that you talked about with the diffusion would explain a frequency difference if I understand well, so long as the kinesin is limiting in the cell. But I don't know, does it explain the smaller number? Because if there's, is it like there's just the residence time in the cell is down and so they can't get loaded as much? Or, but that would imply the frequency and the size of the cargo would be correlated or something like that. So anyway, I just thought I would throw that out.
No, this is a great question. So right, so the big issue is that frequency in principle is the easy thing to comprehend. But as you say, that what's really being regulated is the size of the trains. So how many IFT particles come in together when the train does come in. I think to say we understand that would be way overstating it, but I think we have an idea about it, which is that if you look at the quantitative measurements of the IFT proteins or the kinesins, they sort of co-vary. So when the trains get bigger, they also have more kinesins in them proportionally. So this was my student Will Luddington did this really quite extensively and looked at those traces. And what you can do is you can look at how big a train is. So when an ejection event happens, how big is the event? And then you can also look, instead of just averaging out frequency, you can actually look at the time delay between that event and the next one or the preceding one. And the result is that the more time has elapsed before a train comes in, the bigger the train's going to be. And then the bigger a train that comes in, the more time elapses before the next one comes in. And so in both respects, it's exactly like earthquakes, where you're accumulating something, and then when it goes, the more stuff goes, the less there is left to accumulate. So all the data kind of makes it look like an avalanching system. You see the same kind of dynamics if you look at rice grains falling through a hole in a piece of wood, earthquakes, plasmas, and so on. So the question is, okay, is it just coincidence, or is there actually something that's accumulating? One model is you have all these motors. You have, if the pore is somehow an elastic barrier that you have to push your way through, you could imagine that as more and more motors accumulate, eventually they can push their way through whatever the barrier is. And then if a lot of them happen to go through, now you have to wait longer for the next one. And so that gives you this inverse relation between the frequency and the size of the trains. And just observe data, you get this power law relation between them. And we actually use that in our model. So in the diffusion model, we as kinesin comes back, they accumulate in a pile. And we use basically empirical relations to determine how big of an event comes in when they do come in. So right now, that's kind of a sort of another black box. So even if we convince ourselves that diffusion is relevant, we still don't know quite what's going on with the actual injection process. But maybe this is the way to probe that. But I think, yeah, that to me, that is kind of like the next big unknown thing. And we wave our hands and say, well, it looks like an avalanche, but we would like to know mechanistically what's avalanching. And by the way, we were crucified by reviewers for saying it looks like an avalanche, but that's all we can really say.
So you're working your way from the bottom still?
I guess it's more because people keep adding things to the bottom, and then Oh yeah, could I just do number 11? So what is the
Yeah.
variability of the flagella? Are they very alike within the studied species and between species? So yeah, so we think we can learn. So, it's a classic thing in physics where if you have a model that can explain the average behavior of a system, the next thing you ask, can it also explain the variation of the system? And a lot of times you can explain one, but not the other. So we've been doing some measurements of flagellar variation, both between cells and also within a cell. So the great thing is, because there's two identical flagella, you can ask about fluctuations between the lengths of the two within one cell, but then you can also compare cells to cells to cells and ask how much of variation do you see there? And we do see measurable amounts of both kinds of variation. We can definitely say that some of the variation is definitely due to time variation. So individual flagella are constantly getting fluctuating their length by about plus or minus a micron. We've done some measurements of the magnitude of those fluctuations, which we can fit with other kinds of models. So basically, yeah, they're variable. We see both variation, between the lengths, but also from cell to cell. So some cells, both flagella just will tend to be short. Others, both of them tend to be long. And in that case, the average length of the flagella correlates really nicely with the size of the cell. So bigger cells have longer flagella, and that's probably because they just have more proteins. So they have a bigger pool they can use to build with. So yeah, we have a paper that came out in iScience this past year, which sort of summarizes our study of variation. So I think you can learn a lot from that. Now, what we haven't done yet is look at variation between species. And it is true that if you look at different biflagellate green algae, they can vary quite a lot in how long their flagella are. And one thing that I would love to look at is how does that correlate with the way the cells move? And what I mean is this. So Chlamydomonas can move in two ways. It can swim with its flagella doing a breaststroke motion, but it can also glide over substrate. So if you put them on a piece of dirt, it'll put the flagella out and it'll glide back and forth. And actually it's the IFT motors that drive that gliding. And one thing we found in our study of variation is that for swimming, you swim best when the two flagella are equal in length, right? Which makes sense because you're doing this breaststroke motion. It doesn't matter too much how long they are. If they get too long or too short, they don't swim well, but you can have a lot of correlated variation and still swim, but you can't have them be unequal. But for gliding, you glide best when the flagella are unequal in length. And it's because you have motors pulling on both sides, and the amount of pulling depends on how long they are. So if you have a cell with one really short flagella and one really long one, it'll move in the direction of the long one. And so what would be interesting would be to look for species that rely more on swimming versus more on gliding. Has there been selection for increased or decreased interflagellar length variation? So I think there's a lot to be learned from that. It's something that I keep saying, oh yeah, we should do that, and we just haven't done it. But it would be easy, that's the thing, right? Okay, so yes, and so then there's the question about if there is this avalanching self-organized criticality, should make very clear predictions about the fluctuations and how they scale. And I agree, and I think we haven't investigated that sufficiently. So I have a student who's joined the lab recently who's really good at stochastic processes and that kind of thing. So he's going to probably tackle exactly that kind of question. Okay. Hey, Dave, I'm losing track of which ones I've answered. You want to?
Was that Eric's?
I don't know who asked which of these questions, but yeah, okay, this is a great question. So, right, so the question is, when we talk about essentially, we're talking about equalization of the lengths. I always cast it as competition for a precursor like tubulin or something, but could it be competition for the motors? And I would have to say yes, it could. So I tend not to favor the competition for motors idea for two reasons. One is that if we localize the motors with GFP or something, the vast majority are in the cell body. Only a tiny fraction are actually in the flagella, so that if you remove one, you only reduce the amount very, very, very slightly. That's a very weak argument, I know, but it's just, visually compared to tubulin, where a lot of it is in the flagellum, it seems like one flagellum's fluctuation in the motor would be relatively small compared to the total available pool. That's assuming the total available pool is truly available and not sequestered in some inactive form. It could be that only the ones in the flagellum are able to move and the rest are all just sequestered somewhere. And then the other thing is that when you pop the flagella off and watch it growing back, the new one that grows back has quantitatively the exact, it looks like it has the exact same amount of motor as the previous flagellum had on average. So we don't sort of, again, see a visible depletion of the motor in the flagella. But again, if things are regulated sufficiently, you could still have a competition model and have that happen. So I would say my personal bias is that it's competition for a tubulin, but we don't actually have clear-cut data on that. And I would love to have a better way to do that. I mean, again, this gets back to this: could we modify the quantities of these things? If we could make more of either tubulin or more of the motor, by making more of them, would we alleviate the competition by just everyone just has more? And we don't yet know how to do that. I think there may be some sneaky ways by fusing cells together to transiently increase quantities of things. But right now we don't know. I think that's a fantastic question.
So I think you answered all but 4 and 3 questions.
You have time for about one more too. Sorry, unless you can answer them both really quick.
4 and
Yeah,
3.
well, okay, so how persistent are the motors? They're super persistent. When they go in, they all go to the tip. In Chlamydomonas, other species, they often stop and go back. So that's interesting to think about whether that would that change? Is there some functional reason for doing that in terms of proofreading or something? I like that question. In Chlammy, they're totally persistent. Could we put a trap at the end of the flagella to grab dynein or control the release rate? Yeah, I think you could. So you could use optogenetics, for example, to transiently capture either the dynein or the kinesin. I think that might be an alternative strategy for sort of playing with diffusive return. I like that idea a lot. We haven't done it yet, but it's something that we're looking into how to do.
Does that make you?
Is that all the questions?
I think so. I think that's all that we're.
Wow.
And you're out of time. Let's another one. No, I think that's it.
Wallace, thank you.
Thanks so much for these amazing questions. This was great.
That was great. And I apologize that in Zoom, it really only just sounds like one person's clapping for you, but yay.
I'm
That
clapping.
was wonderful. Thank you.
Thanks, everybody. I really appreciate this. It was fun.
Excellent. So I want to go ahead and just show you what's going to happen next. So I'm going to share my screen for just a minute. We are going to go to lunch or have a lunch-ish break. If you're in California, it might be like an early coffee break. But we're going to take a break in just a minute. So I just wanted to show you what the signups look like that we kept talking about over lunch. So if you head, pardon me, to Monday, lunch break concurrent sessions, these are the 3 sessions that you can choose, either a one-on-one conversation with a modeler or one of the workshops. All you need to do is click on this. We've put the bios, we've listed the bios that we have for those speakers, and you just click to sign up. This is limited to 1, just a reminder. So please only sign up for the one-on-one conversations with a modeler if you know you can make it, because they are very limited in space. And the concurrent sessions, we've listed a little bit about them, and then you just sign up right there on that bottom Post-it note. You just kind of click with your name to sign up, and that's it. So I wanted to let you know that. I'm going to do a new screen share to just talk about how lunch is next. So we are going to reconvene at 1:30 Eastern time. It's a little over a 40-minute break. Just as a note, we're going to stay here for a couple minutes to answer any questions that you might have. But right before we start the next session at that 1:30 Eastern time, just know that it's kind of like clearing your cache, if you will. We just kind of close the meeting down really quick and then fire it right back up. So if you happen to come back and you're like, wait, it's closed, just give us 30 seconds to a minute and we'll open it right back up. But it's just kind of a nice practice to do every once in a while. So we're going to do that. So thank you again, Wallace, for a wonderful kickstart to our conference. It was lovely and nice to see you as well. And for everyone else, if you don't have questions, we will see you back here at 1:30 Eastern time. Thanks. Hello, everyone. Welcome back, and thank you for joining us. I always get super excited about these sessions, so I hope that you...
Can we get some emojis? Did you meet some new people? Yes, thumbs up for those that, yes, awesome. Good, good, good. Hopefully these will be some potential collaborators as the week continues, and you will also have the opportunity to meet more new people as we go throughout the week. So a couple things that we'd like to share with you in preparation for tomorrow. So before we go, can everyone see my screen? Donalyn, can you see that? Awesome. So just a friendly reminder that tomorrow morning we will start with our lightning talks at 9 a.m. So please join us for that. We have a few presentations starting from 9 to 9:30, and then we'll have an opportunity to have some follow-up discussions with those presenters. Also, just note that you do not need to sign up for those lightning talks. They're not like the concurrent sessions. Please make sure you take some time this afternoon or evening to check some of these abstracts out. And we also want to remind you that if you have not signed up for any of the concurrent sessions, whether Meet the Modeler or concurrent session 1 or 2, please do so by tomorrow. Those will take place tomorrow afternoon. So we want to make sure that we have folks situated for that. And lastly, if you met some people today and want to continue that conversation, we do have our networking lounge open. And so that is our Wonder Room, and that's what we shared a bit earlier today. So if you actually go to the Chi-Storm page, you will see on here that there is a page that says on the left-hand side of the menu, Networking Lounge. And if you click on that and click on Join Wonder, it will take you directly to that link. So that will be open again for you throughout the entire conference, 24 hours a day, between now and Friday, so you can connect with people and probably even head over right after this is done and connect in one of our famous 80s movies rooms. And did I forget anything else, Donalyn? Is that it? Okay, awesome. So without further ado, I would like to pass it on to David Stone to close us out for the day.
Is that me? Am I live?
You are so live.
Okay, well, first of all, I just want to, just to be sure, emphasize those lightning talks are 9 a.m. Eastern time. So your Chi-Storm link should give you local time, but just Jocelyn said 9 a.m. So in case anybody's just a little bit sleepy, be sure to make the time correction if you're not on the East Coast. And the Wonder Room, whenever I have tried to go directly from Safari to the Wonder Room, it has told me I have to use Google Chrome. So it gives me a link to paste into Google Chrome. Maybe that's just my computer, I don't know, but don't be surprised if you're given a link, if you're not using Chrome. And paste it into Chrome and you'll get to the Wonder Room. I know this because I went to the Wonder Room a couple times over the weekend. That's how sad my life is. No one was there. Closing remarks. KI, No Innovation, has told me that every day I have to come up with some wise and wonderful, deeply observant, meaningful closing remarks. I have none today. I think it was a great day. I learned a lot. Mostly I learned how much I have yet to learn about modeling. But I felt, I went to a total of 4 posters and there were active discussions going on in each of those sessions, which I thought was great. I actually thought that was a lot better poster session than any real poster session I've ever been to. So thank you, KI, for arranging all that. I guess the only other thing I have to say is the pubs on Taylor Street are open. And if you guys were here, we could adjourn. If you're nearby, start driving, meet you there at 6. And otherwise, see everyone tomorrow. Does anyone else have any closing remark they'd like to offer? No one? All right, Jocelyn, say good night.
Good night, everyone.
Good night, everyone.
See you tomorrow, 9 a.m. Eastern time.
Bye, everybody.
Bye. Thank you.